if I keep x2, x3, x4 and xn constant, then by increasing x1 by 1 unit, how much change in y will occur? This beta 1, this value of beta 1 tells you that much change in y will occur if you change this variable x1 by 1 unit. However, we are keeping all others constant. We are not changing x2, x3, x4. We are keeping them constant, whatever their values are. If I increase or decrease the x1 by 1 unit, then the change in y will be equal to beta 1. Understood? This symbol here is the error symbol, which means something which is not explained by your variable. It's not always necessary that we get a very strong, a very not reliable, but a very strong and an ideal model. Always it's not possible. We always have some errors. We always have something which is not being explained by our independent variables. The variation in the dependent variable is not being explained by our independent variables. And this error term captures that. And how do we practically see this error term? This is included here in equation. However, when you will develop the regression analysis, or when you conduct the regression analysis, or when you will develop the regression equation, you won't see that error there physically. But how this error is being explained, we'll see in our next few slides. But just tell me quickly, have you got the concept so far? Is it clear so far? Because this is a very important concept, how to interpret. We'll do it when we'll do the SPSS. I'll show you how to interpret a regression model. But so far, is it clear to you? Everything is clear to you? Okay. So here, this figure tells you what that error term is. This line over here is your, we say it's just a straight line that I drew here, which tells me that where my dependent variables are falling. So all these dots, let's say that my this blue dot is the actual value of y, is the actual value of the dependent variable. This line, I got this line from my regression model. This black line, this diagonal line, I got it from my regression model. So any point on this against y is the estimated value of y from the model. So y hat is the estimated value which falls on this line, and this blue dot is the actual value, is the observed value of y that I got from the field. Then the difference between this estimated value and this actual value, or the observed value, is the error, or we call it residual. When you will do the analysis, when you talk about regression analysis, we call that error as residual, which means something which is not being explained by our model. So the purpose of our linear, when we do these regression models, what our purpose is to minimize this distance, minimize this difference, to get a model so that the difference between the value that we estimated using the regression equation and our observed value for the same value of x. Remember this. So for example, when we have this speed limit as 50, then for that the actual value, the observed value, and the estimated value for that speed limit of 50, the difference between those two should be minimum. We try to minimize that difference. That is, if the minimum the difference is, the stronger the model is. The maximum the differences are, or the more the residuals are, or the more the errors are, the weaker the model is, the less reliable the model is. So our simple, in our regression analysis, that is what, based on our data set, based on the way we have all the variables set up, our tool tries to minimize the difference, tries to give us a model in which the difference between the estimated value of y based on the equation and the actual value of y is minimum. Okay? So, the amount of variation in dependent variable explained by independent variable is determined by coefficient of determination denoted by R square. Now, when we were discussing the correlation analysis, we said that the value of R tells us what is the strength of the relationship between our dependent and independent variables. How can we tell that in terms of a regression model? How can we say that a regression model, whether it's a strong model, whether it's a weak model? That is, we come to know that by knowing the coefficient of determination, or R square. The value of R square may range between, again, 0 and 1. So the higher the value of R square, the stronger the model is, which means there are independent variables are capable of, or we have selected the right independent variables that explain the maximum variation in our in a dependent variable, or how our dependent variable is varying, how much, like how it's decreasing, how it's increasing, where it's increasing, where it's decreasing. That variation is being very well explained by our independent variables. If that is the case, then for that regression model, our R square will be closer to 1. Then we have R square as 0, which means our independent variables are not able to explain any variation in our dependent variable. As close as it gets to 1, the stronger is the relationship. And you will see that when you do the SPSS, it will give you a value of R square, and it will tell you that how stronger the relation, how effectively, how strongly all the independent variables are able to explain the variation in our dependent variable. So the closer the value of R square to 1, the stronger is the prediction power of the regression model. The value of 0 for R square means no explanatory power of the model. So when you have 0, which means your model is good for nothing, we should better try some other model, or maybe it's in case if you develop a simple linear regression model and your R square value is, let's say, 0.35, which means this linear line, this linear model is not able to explain the variation in your dependent variable in your data set effectively. So then you may try maybe a log model, or maybe some other model, a model with a power model, and in that case the value of R square will get stronger. So that this is an indication, the R square is an indication. It tells you what is the power of your model, whether it's strong, whether it's weak. And keep in mind that the value of R square is always positive. Unlike the coefficient correlation, it cannot be negative or positive, because it's not giving you the sense of direction of the relationship. It's just giving you the strength of the relationship. It's just telling you that how much variation in your dependent variable is being explained by your all your independent variables. So it's always positive. Now, whenever we develop some models, we have some basic assumptions based on which we develop the models. And the reason I'm discussing these assumptions is because when we do a regression analysis, we do the test, we do a check to see if these assumptions are met or not. So first of our assumption is that all the errors that we get, all the residuals that we have after we develop our model and then we find out the residuals, then all the residuals or something which is not being explained by your model, they are normally distributed. This is one assumption. Number two, that errors have constant variance, which means that the errors are randomly distributed. They are at a constant distance from the mean. It's not that they are following some pattern. If the variance is if the errors are following some patterns, which means that there is some problem in your data set. Maybe there are some outliers. Maybe the relationship between your dependent and independent variable is not linear. So we make all these checks to make sure that the model that we have developed is good, is what we need, we should have. So, and then that explanatory, the third assumption, which is a very basic assumption, is that all the independent variables or explanatory variables, or the variables that explain the variation in our dependent variable, are measured without error. Of course, it is not always possible, but this is an assumption. Make sure that this is an assumption. It's not always possible that we measure something without errors. However, we try our best. I mean, in our knowledge, we did not make an error. So if we come to know that while collecting the data set we made an error, we try not to use those numbers, or we can always go back and then reduce those errors, or trying to control our experiment so that all the independent variables, or of course the dependent variable as well, are measured without error. So in our knowledge, what we should know is that we haven't made errors while collecting the data set. If there are any errors, then we try to minimize them, but we do not do errors intentionally. And then all of the unexplained variation is confined to the response variable, which means anything which is not being explained by our model, anything which is not being explained by our independent variables, is only confined to the explanatory variables, which means we have collected a set of our best independent variables that explain the variation in our dependent variables, and whatever is left is just confined to our dependent variables. So these are different assumptions that we have while we are developing a regression model. Now, the thing, if you remember from our last lecture, we discussed the t-test. Again, that comes back. Now, how would I know? Okay, so for example, I collected 5 independent. I developed a model that has the 5 independent variables, and my coefficient of determination, or R-square value, is 0.98. But is 0.98 is the true value, or like really all my independent variables are explaining the variation in my dependent variable? How would I know that? How would I know that this is, how would I validate validation is something different, but how would I be confident about my independent variables? Because the regression is the type of model that the more independent variable you will have, the more coefficient of determination it will get stronger, or R-square will be higher. However, it's not always the case that all your independent variables are contributing to explain the variation in your dependent variable. And how do we know that? We conduct a t-test. Well, we don't. While you are using the SPSS, you don't conduct a t-test. It does that for you. But if we are talking manually, then how do we find out that all the independent variables are significant? They are explaining the variation, and they are not there just as dummy variables. So significance of a predictor or an independent variable in a regression model is determined by conducting a hypothesis test about the regression coefficient beta I. We saw the beta I is there, and we conduct a t-test, and our hypothesis is that these beta I, or these independent variables, are not contributing anything. So our alternative hypothesis, or H0, is that an independent variable xi is not. Okay, what should I do now? Is it okay now? Is it okay, or is it still bad? Okay, so our null hypothesis is that the independent variable is not explaining any variation in our of our dependent variables. That is our null hypothesis, which means that beta I is equal to 0, meaning there is no relationship between the dependent variable and the independent variable.